Short video lecture on the supercell thunderstorm. Why do we want to talk about that? Let's talk about an ordinary thunderstorm first. And the reason that we care about a thunderstorm is its hazards are worrisome to us. Strong damaging winds, large hail, tornadoes, lightning, flash flooding, all on that list. But a thunderstorm, of course, by definition has lightning in the accompanying thunder somewhere. But does that mean that all thunderstorms are severe? And the answer is no. One estimation is that about 10% of storms in the U.S. are actually severe by these definitions: winds greater than 58 miles per hour, or hail larger than 1 inch in diameter, or a tornado. Flooding, flash flooding, a little more complicated. The storm itself can be producing heavy rain, but there are other factors on the ground that determine whether it's actually going to produce a flash flood. And lightning has no formal definition for severity, except to say that all lightning that hits the ground is severe by definition. But in terms of frequency, or trying to figure out, if one thunderstorm has greater cloud-to-ground potential than another, there is no official criteria set for that. A thunderstorm's basic needs are a moisture supply, enough humidity to at least produce the cloud, unstable air that when lifted wants to accelerate away from its original starting point, and a source of lift, like a front, a low pressure area, dry line. But for severe storms, you need to up the ante a little bit. You need highly unstable air. We're starting to get into thermodynamics, how unstable is the air. And also favorable wind shear, winds which change with increasing height in a way which gives a storm better structure and the potential to rotate. So these two items in combination give rise to a special type of thunderstorm known as the supercell. Storms that survive longer have a better chance of producing severe weather. So supercells tend to have several distinctive radar patterns. They contain mesocyclones, as the rotation mesocyclone means small low, and they generally move differently because they are a different type of storm. Instead of being controlled by the flow, they actually produce some feedback back to the flow and kind of buck against it a little bit. Supercells are frequent producers of large hail, strong winds, and tornadoes. A classic supercell is tilted. Here's the key to understanding why a supercell can survive so long. Because at the end, the precipitation and the downdraft it's connected to are away from the incoming updraft, which is the energy source for a storm. So one's not choking off the other. And another feature of a supercell storm, it is rotating. And among other things, that's a necessity for strong tornado development. Here's a real quick schematic of what I'm talking about. Typically, the winds in the atmosphere are structured so that they're slower down low, faster up high near the anvil. And there's a tilt, and you can see the updraft and the downdraft are separated from each other and allows this storm to have kind of a super life. This is kind of a cool shot. This is a three-dimensional radar shot. All you need to know about this is greens are heading toward the radar site marked in white, reds are moving away. And you can see a counterclockwise kind of torque or spin there, an implied rotation. And you can also see the tilt of this particular supercell thunderstorm, which is producing a tornado as this image was taken between Republic and Clever, Missouri, in Christian County on the infamous May 4, 2003 outbreak. You can also, in dry air, see the helical shape of the thunderstorms without a lot of clouds getting in the way. Perfect shot of that. Here's a schematic of a supercell storm. We'll start with the overshooting top. You often see this in the distance. The updrafts have such an acceleration they go past the level where they're neutrally buoyant and keep going. Their inertia carries them up. They eventually sink back down. They may overshoot again. It's a sign of a very strong thunderstorm with powerful updrafts that can buck against the stable layer that they hit at the tropopause. Mammatus clouds, as circled here, are on the front side of the anvil, but typically they're observed maybe more often on the back-sheared anvil side. And Mammatus clouds are not dangerous in and of themselves, but they are, again, indicative of a very unstable storm. The forward flank gust front, rush of cool air followed by rain, then heavy rain and wind, shelf clouds, roll clouds. We're probably very familiar with the forward flank gust front aspect of a thunderstorm. Then there's the hail cores near the updraft-downdraft intersection, the tornado in that same area, if there is going to be one, or a wall cloud precursor to a tornado. And then there's the rear flank downdraft, which is a different type of downdraft, and we'll talk about that more when we talk about tornado genesis. And finally, here's the supercell view from aloft with all the components we just talked about, only now you're looking down on it from above. Supercell, again, a very important concept to understand in severe weather production.